In this video, we're going to cover a concept called antiderivatives. And basically what that means is we are going to reverse the whole derivative process. Now first, the definition of an antiderivative is any function that if you take the derivative, you're going to get to the one that is desired. Now what do I mean by that? If I start out with, say, the function f of x is cosine x, and I said, okay, everyone, think of a function that you know of whose derivative gives you the answer cosine x. That's what we're going to call our antiderivative. And most of you would probably say, well, capital F of x is going to be sine x. And that is correct because the derivative of that gives you cosine x, which is what we are trying to get. So that means the antiderivative of cosine x is sine x. With that said, however, what if, for example, me, I'm difficult, I did not give the answer sine x. I said, let's do sine x plus 4, because 4 is a great number. I love 4, so I'm going to put it in my answer. And you say, well, no, you're wrong, because that's not the right function. Well, if you check here, if you check what the derivative of this is, you also get cosine x, which means you're not wrong, and also I'm not wrong. We're both right. We both have a perfectly valid antiderivative. Well, in fact, what if someone else had a different favorite number? What if they put 17 or 29 or whatever other number they feel like using there? Well, all of you would be right, and so what we'd like to do is we'd like to find something called the most general antiderivative. And we need to realize that you could put whatever plus a number you wanted there, any number at all. And so we're going to just write the following here. First off, this symbol, this weird squiggly line, this weird dx thing, we will explain that more in the future. But just for right now, that symbol means the most general antiderivative. And the most general antiderivative of cosine x would be sine x plus some number c. Okay, so that is our most general antiderivative of cosine. Now what if we want to do something like that with a more complicated function here? So I gave you a bunch of things here. It turns out that when you're adding or subtracting, you can just look at each part separately. So you might say, what function gives you a derivative of 2x? Well, that would be x squared. What function gives you a derivative of e to the x? That would just be e to the x as well. And what function gives you a derivative of cosine x? We already saw that. That is going to be sine x. And then we don't forget our plus c there. And this would be the full correct answer. Now I do want to say that a lot of times I'll see students forgetting the plus c, and then they lose, a point on their tests and so on, because it's a very common mistake. So try not to do that. Try not to forget it, because you always need that whenever you're trying to get the most general antiderivative. Now the second one is going to be quite a bit more challenging. I'm actually going to skip over some of the reasoning for now, because we're going to see in more detail in a future video how I came up with this. But it turns out that the answer is going to be 1 over ln 3 times 3 to the x minus cotangent x plus 2/3 x to the 3 halves plus c. Now again, that probably seems like it's coming out of nowhere, and it is right now. But you can double check that I'm right by taking the derivative of all of that and seeing if it matches what's inside. And unless I made a mistake, it will match. However, again, I'm not explaining right now where I came up with those things, but we will see in a future video rules by which you could do that you could get those answers. Just for right now, I'm just leaving it as, accept this and we'll move on. Well, now that we have this idea of an antiderivative, what can we use it for? Well, one thing we can use it for is that if we're in a situation where we know the derivative of a function and we know what y value it had at some point in time, it turns out we can then use that information to find what the formula for the original function is. Now, this might seem strange to you. You might say, well, how in the world are we going to have the derivative if we don't have the original function? Well, it turns out that quite often we can get the derivative just by measurement. We can say, okay, here's how the temperature has been changing over time, and we can then go ahead and just see how does it change each day, use that as part of our derivative there, right? Changing is derivative, and then we can use this process to find a formula for temperature. Again, that was a very rough idea of it, but it turns out knowing the derivative is actually not that hard compared to knowing the original function sometimes. So in this case, we know the derivative is secant x tangent x plus x. So we ask ourselves, well, okay, what function would have a derivative secant x tangent x? And we should know that that function would be secant x. And what function would have a derivative of x? Well, that would be 1/2 x squared. And then we know that since it's an antiderivative we don't know the value of, it's going to have some sort of a plus c here. But we know that if you plug in 0 into this function, you're supposed to get the answer 5. Now secant of 0 is 1, this is 0, and so we found that c is 4. However, we don't just box that as our answer. That's not our answer. Our answer is the function, which is going to be secant x plus 1/2 x squared plus 4. So you see, by knowing the derivative and by knowing the value of the function at one point, we were able to find the c, and knowing that, we then had a formula for the function. Now for this second one here, we actually have a really cool application of this exact type of problem. And the idea is we're going to say, well, what happens if you have an object that's falling? Well, we know that when you have an object that's falling, we know the acceleration is -32. Well, acceleration in math concepts is the second derivative of where you're at, the height. So I'll call height as, say, h of t here. Then the second derivative is always the acceleration, so that would be -32. So then what we could do is we could reverse this. We could say, well, if that's the second derivative is, if I find the antiderivative, I'd find the first derivative. So we ask ourselves, what function is derivative going to be -32? Well, that would be the function -32 t plus some constant here. Then we know that it says that the initial velocity is v0, but velocity is just the velocity of speed, it's just the first derivative here. So we find our c value is v0, so that means h prime of t is -32t plus v0. And now we know the derivative, so we can do the antiderivative one more time. We'd get -16t squared plus v0 t plus some other new c here. It's different from the old c. And we know that the initial height is h0. This means my new c is h0. And then what you get is the following formula, -16t squared plus v0t plus h0. And this formula right here will tell you how high your object is off the ground at any time point. And all you have to know are two things. You have to know how high did the object start and how fast was the object going when it started. As long as you know those two things, you are going to be able to then use this formula to find out how high it is at any given time. And even better, if you know how high it is, then what would it mean for h of t to be 0? That would mean that it's not off the ground at all. And so if you just plug it h of t equals 0 and you solve with the quadratic formula, you can then see how long it's going to take for an object to fall to the ground. So it's a really cool application of this antiderivative concept that now you could figure out, by just doing a couple of quick formulas, how long it takes any object to hit the ground once you throw it. And they use things like this in order to figure out, for example, when you throw a baseball, where is it going to land, or all sorts of guns. If you want to find out where the bullet's going to land, cannons. It's all based on this knowledge right here, and so we see some really nice applications of calculus to the real world.